All right, so let's go ahead and jump right into it. Multiple linear regression. So I'm going to approach this very similar to what I did the first simple linear regression video, and then I'm going to answer the questions. But let's see how this goes. Let's just see how it goes. So with multiple linear regression, the only thing different from multiple linear regression to simple linear regression is that you have multiple explanatory variables. You have multiple explanatory variables. And in this first interaction, we're only going to deal with the situation where all of our explanatory variables are quantitative. So let's look at it like this. So here is our data. At least this is a summarization of our data. We're going to let we're going to let median value of the home be our response variable, right? And then crime, average room amounts, and age is going to be the actual explanatory variables. So these three are the explanatory variables, and then this is going to be my response. Okay. In the description, I'll tell you in some way, shape, or form what's the response variable, and then you can figure out what are the remaining the variables that I provide, which would therefore be the explanatory variables. Important note here, things to note is the min and the max. I'm providing you the min and max so that you can know what values you're able to make predictions with. Okay, what values you're able to make predictions with. So if the average crime is 100, you can't make that prediction. Okay. We can then look at the correlation matrix. And the correlation matrix allows you to measure the linear relationship between the quantitative variables. So this value, this negative 0.38, is the relationship between crime and median values. That makes sense, right? So the more crime you have, the less the home will be. This value is the same as this value because it's just a mirror along the diagonal, meaning that this is the relationship between crime and median value. This is the relationship between median value and crime. Okay. This also shows me the relationship between median value and average number of rooms, and then this is the average age and the median value. Okay, so the older it is, it's not valued, the lower the value. That makes sense as well. Okay, so this is a correlation matrix. Okay, and again, along the diagonal is a mirror. Okay, all right. So with that being said, I can create a visualization of the same information. And so let's do some deeper learning on what's going on here in this visualization. So on the bottom left, let me say, let's do it like that. The bottom left triangle shows the relationship between all the variables. So this is the median value of a home, and then this is the crime. So this is the general plot of median value and crime. So this is median value in room, and this is the median value in age. Okay. Another thing to know is that along the diagonal here, it just shows you the distribution of that one variable. Median value, this is crime, this is room, and this is age. It's just the distribution as if it were to be a histogram. And then finally, it shows the correlation between crime and median value, which is what we see here. Okay, this is the correlation between room and median value, which is what we see here. So this is a positive association. It's positive 0.695. This is a negative association. This is negative 0.388, negative association. Okay. All right. With that being said, that's it for this plot. I mean, you can see the other numbers and how they match as well. Last but not least is the analysis. Okay. So here we have the analysis. We have the following explanatory variables: crime, room, and age. So this is another way of me telling you what the explanatory variables are. Okay, take note of that. And then my response variable is going to be median value. Okay, take note of that. Again, we're going to ignore these and ignore the residuals, the file number summary. And then I'm going to highlight that these values, okay, this negative 23.60 is going to be my y-intercept. This is my regression coefficient. It's no longer a slope. This is going to be my regression coefficient for negatives for crime, my regression coefficient for room, my regression coefficient for age. These are all the corresponding standard errors, the measure of variability from sample to sample. These are the test statistics. These are the p-values. Okay. The standard deviation residuals is still important, 6.094, which is the amount of variability that's left unexplained by the regression model. And instead of using multiple R squared, when we use or talk about or use multiple linear regression, we use the adjusted R squared. And I'll talk more about that next week. We're going to use adjusted R squared. We're also going to emphasize the F statistic in multiple linear regression and the corresponding p-value, this p-value here. So we'll talk about this in an upcoming video. I think maybe not this video. I don't think so. Oh no, we will. We'll talk about F statistic this video. Yes, we will. And then we'll talk about multicollinearity, okay, in a little bit. So in answering the question, just know that this exists. So that's just the SSVA, summary statistics, visualization, and then the analysis. And I'm going to take a quick break. And y'all should too before we answer some of these questions, okay? All right, so let's finish these questions. So state the variables. Ideally, you would have specified the variables that we dealt with or mentioned earlier: crime, average room age, and the other one, as well as median value of the home. And so they're all quantitative. Age, crime, and room. I did say that. My apologies. And specify what's the explanatory variable. Order doesn't matter here. And then that's that. From there, next question says, how do we visualize the relationship between two quantitative variables? A scatter plot. And says, how many pairs are there? Including the response variable, it should be 4, choose 2, because there's 4 options, choose 2. So it's 4 factorial divided by 2 factorial divided by 2 factorial. So it should be 6. 4 times 4 times 3. Yeah, it's going to be 6. Okay. How do we measure the relationship between linear relationship? So key here is linear relationship between two quantitative variables. We use correlation, which is in between 0 and 1. I mean, negative 1 and 1. Ooh, oh my gosh, negative 1 and 1 caught me almost there. You know that the correlation, you can change the scale, which is fine. That's when you can apply transformations to it. That's what I mentioned in 2 videos ago. And then what is the correlation matrix? The correlation matrix allows you to see all the correlations between each pair. Okay, each pair. That's what we saw in terms of the numbers. All right. So not relationship, linear relationship. Measures the linear relationship. All right, so I think that's it. I already said the answers. Okay. Okay. Yeah, so scatter plot is used to visualize the relationship between two quantitative variables. The number of variables times the number of variables minus 1 over 2. That's essentially 4, choose 2. And it gives us 6. Pearson correlation measures the linear relationship between two quantitative variables. Okay, to be negative 1 and 1. Correlation matrix displays the linear relationship metrics for each pair of quantitative variables. Okay, So that's question 2. These questions don't get quite hairy pretty fast. Write the regression model from our output. So remember that regression model up here involving these estimates. That's what I'm asking for. Okay. And so this is how I wrote it. Okay. So y I hat is equal to negative 23.61, minus 0.21 times x1I to delineate crime, 8.03 times x2I to delineate age, and negative 0.05 to delineate age, crime. I always forget it. What's the last one? So first is room, then it's age. Okay. That's fine. Then I actually provide an interpretation. So there's a couple things to note here. One of the first things to note is that you can't have an average median value to be negative. It can't be. You can't have a value. It can't be negative. So logically speaking, in this context, it doesn't make sense. Okay, it doesn't make sense. So take note of that. And then there's going to be something a little bit special when interpreting these 3 values. Okay, these 3 values. So let's go ahead and begin. So the first one, like I said, regarding the y-intercept, that's when all room, crime, and age are equal to 0. The average median value of a home is negative 23.61. But remember, that's not possible, which is uninterpretable because the average home cannot be negative. Okay. Now to interpret the regression coefficient, remember that's what we called it, the regression coefficient for crime. That's going to be, as crime increases by 1 unit, the median home value would decrease by negative 21 or negative 0.21 on average. But now you have to say something in addition. Okay, on average, while holding room and age variables constant. So you have to hold the other 2 explanatory variables constant when interpreting the regression coefficients. 0.21, negative 0.21. Okay, so you can imagine the next 2 interpretations, 8.03 and negative 0.05, is the same thing, or very similar at least, but you have to hold crime and age constant, and then finally room and crime constant. So as room increases by 1 unit, the median value of a home increases by 8.03 on average, while holding crime and age variables constant. And the same thing can be said for age. All right, so let's move right along. So then remember, one of the purposes for regression is to make predictions. Okay, it's to make predictions. So here, given this particular model, multiple regression model, we're using these explanatory variables to predict median value on the Boston housing data set. Suppose we have a suburb with 25 per capita, average room dwelling is 6, and the proportion of homes built before 1940 is 35%. So what you would do is you would confirm that you have values in between the min and max. Okay, right here. I believe it was 6 homes, 6 rooms. I think the average is 30 something. I could be wrong. And the proportion is 36 or 35. Okay. So we should be good with all the variables. It notes how the age, I think it's the proportion, it's written as a whole number. It's not as a decimal. So that's how you'd have to input it into your equation. So what do I mean by inputting it into your equation is by doing the following steps. So you state the y-intercept, state 25, I think 25, 6, and then 35, and then multiply by the regression coefficients. Okay. You get 17.57. So 17.57 is what we predicted. However, how do you interpret that value? Okay, how would you interpret that value? When a home has a set explanatory variables 25% the crime rate, 6 average rooms per dwelling, and the proportion of owner occupied units is 35%, the average median home value is 17.57 thousands of dollars. Because remember, it's in units of thousands of dollars. Okay? That should be pretty straightforward. So the thing is, if you have a question like, oh, what if it's outside the range? Therefore, then you can't make that prediction. If one of them is outside the range, say for example, this was 10. I think it was 8.09 was the highest, I think. Then you can't make that prediction. Okay? And assuming everything else was the same. All right. So question number 5. Okay. We have a model that's trying to predict the median value of owner occupied homes, okay, based on the following explanatory variables. This is done using multiple linear regression, okay. The omnibus test. So now it's time to talk about that F value. The F value. So the omnibus test is a way to check if our model as a whole is useful. It's asking, does these factors or explanatory variables together help predict the median value of homes? So in a way, this is kind of like a NOVA test where we're legitimately seeing if any of the explanatory variables is different. In this case, if any of the explanatory variables has a linear relationship with the response variable, or in one way ANOVA, you just want to see if one group is different from the other. So rewind, I'll say it again, rewind it if you need to, but what we're trying to see with the omnibus test is to determine if at least one of the explanatory variables has a linear relationship with the response variable. Okay, so therefore, we're going to write our non-alternative hypotheses as well as the degrees of freedom and write a conclusion. But my null hypothesis is that they don't have a linear relationship. None of them do. Whereas my alternative is that at least one of them does. Okay. So K is the number of explanatory variables, N is the sample size, but my null hypothesis is that beta 1 is equal to beta 2 is equal to beta 3 is equal to 0. So that means none of them have a linear relationship. None of the explanatory variables has a linear relationship with the response. Whereas my alternative is that at least one. Okay, there's no way to write it in symbols. Okay. You just need one. And so in terms of writing this out, all the explanatory variables do not have a linear relationship with the response variable. In the context of the problem, I say crime, age, and room do not have a linear relationship with the median value of a home. Whereas the alternative hypothesis, at least one of the explanatory variables has a linear relationship with the response variable. And then in the context, at least one of the explanatory variables has a linear relationship with the median value of a home. Okay, so the test statistic, I'm gonna go up for this so you can see where it's actually situated. It's right here, the bottom, right? Right here, it's the bottom of the R output. This is my test statistic. Okay, these are my degrees of freedom. I'm not highlighting this in this quarter, but this is my p-value. Okay, that's what I'm highlighting that. So we're gonna do what to our null hypothesis with such a p-value. Okay, if you said reject it, that is, you're gonna reject that null hypothesis. You're going to reject this claim. At least one of the explanatory variables has a linear relationship with the response variable. All right. And so then this is the conclusion. We reject the null hypothesis, at least one, indicating at least one of the explanatory variables, crime, age, room, has a linear relationship with median home value. Number 6, now we can specify, or at least we can test. I'm only going to do one, but now we can test which of the explanatory variables has a linear relationship with the response variable. So it's kind of like a post hoc method now. So state the null and alternative hypothesis for crime regression coefficient, say the statistic, state the p-value and the decision regarding the null hypothesis. And I also do a 95% confidence interval as well. Okay. So this is our null, okay? Same thing as before, that there's no linear relationship for our null. An alternative is that there is a linear relationship, and then words can be seen as this, okay? Pause if you need to and write this down. All right, and then our test statistic, as we saw in the past, is going to be our actual coefficient divided by the standard error, which gives us 6.195. And our p-value is 1.22 times 10 to the negative 9. So where am I getting this information from? If you don't remember, it is right here. So this is my test statistic. This is my corresponding standard error. If I take this value divided by this value, I get this value. And then this is the p-value. So I could have done this for all of them, which it does it for us. And we know that all of these explanatory variables has a linear relationship with the response. Okay, which is nice. Okay, that's that, we're there. And then in terms of creating a confidence interval, this is the logic, right? This is the equation. But remember, when it comes to creating a confidence interval for a regression coefficient, 0 has special meaning. Do you think 0 should be within the lower bound, upper bound? If you said no, you're correct. Okay, no, 0 should not be based off of this, right? So it's my point estimate, my critical value, my standard error. And so you can see both of these lower bound and upper bound does not include 0. They're both negative. Okay, and that should make sense. That should make sense based off of what we noticed about when we reject the claim that beta 1 is equal to 0. Okay. All right. So state the standard deviation of residuals. The standard deviation of the residuals is in the same location as it was before for simple linear regression, which is, I think in this case, 6.09594. What does the standard deviation of residual mean? It means, there's a lot of different ways of saying this. One way of saying this, again, you can be quizzed on this because I already put in a quiz for the last quiz, is how far does how much variability is left unexplained by the model? Okay, left unexplained. How much variability is left unexplained by the model on average? Okay, how much variability is left unexplained? Another way of saying the same exact thing is how far does each point deviate from the regression equation? In simple linear regression, you would have said regression in line. I didn't mention this, but it works the same logic. How far does each point deviate from the regression line on average? Okay. And why this is important, because it tells us how well the model performed. How well the model performed. So if all the points were on the line, oh, this is the quiz question. If all the points were on the line, then the standard deviation residual would be 0. Okay, the standard deviation residual would be 0. But if all the points are far, far from the line, there's a more amount of variability that's left unexplained. Okay, so that's that. All right, so then let's go to question 8. State the adjusted R squared. Okay, the adjusted R squared is, I think, 0.56. You saw that from the R output. What does it measure? It measures the proportion of variability explained. It measures the proportion of variability explained by the regression model. Okay, so in the back of your mind, it's like, why do we use adjusted R squared here and R squared in simple linear regression? And the rationale for that is because with regards to adjusted R squared, it allows you to account for more variables. So come to find out, if you just add regression, if you add explanatory variables to the model, your R squared will increase. So what adjusted R squared allows us to do is to penalize the actual regression model to adding variables that may not necessarily explain more variability. So that's why we use adjusted R squared, because it penalizes the R squared for potentially adding variables that does not explain more variability in the regression model. I know that's a lot. You can rewind that again. All right. So measures the proportion of variability in response that's explained by the explanatory variable. Adjusted R squared accounts for the multiple explanatory variables within the regression models, whereas R squared does not. That's an abbreviated version, because we're penalizing R squared for adding explanatory variables that may not necessarily explain more variability. Okay. Last but not least, what would there be an issue if the explanatory variables were correlated? Okay. The idea is that, is there an issue if the actual explanatory variables between one another have a relationship? And the answer to that is yes, that's the problem. Okay. So if so, what problems could this cause? That gives you an overinflated regression model. You think the regression model is not um as good at predicting that as we may think, because it has an inflated sense of power regarding, no, not power, but ability to make predictions, where in reality it's not that good. And so what we call that, what we call when the explanatory variables are correlated, is multicollinearity. Okay, multicollinearity is when we say that there is a relationship between the explanatory variables. How do we measure multicollinearity is something called the variance inflation factor, VIF. Okay, so the VIF legitimately is going to be in between 1 and infinity. Okay, the closer to infinity, the more problematic it is. Okay, ideally we want our VIF scores to be between 1 and 4. We want our VIF scores to be between 1 and 4. And if you saw, all our VIF scores are in between, or just around 1. Okay, so there's not a problem of multicollinearity here. Okay, so with that being said, would there be an issue if the explanatory variables were correlated? Yes, but I didn't provide anything else other than that, because I was just explaining it. So I'm just going to type it here. VIF is not a problem here. All right. Then the question 10 is pretty straightforward. What is the difference between multiple linear regression and simple linear regression? And all it really is that multiple linear regression has multiple explanatory variables, whereas simple linear regression has just one explanatory variable. And that's it. We'll do more with multiple linear regression next week. Thank you.